Hello everyone, welcome back. I want to take some time today to kind of go through the ANSI B11.TR4 or the ANSI B11 Technical Report number 4, published in 2004. I want to go through this because this gives us kind of a rough understanding of the programmable electronic system or programmable controller or PLC that you would be using for your safety control systems to meet your ANSI B11 standard of safety control. So the ANSI B11, and again, just like we did on any of our other ANSI B11 standards, it's always helpful if you have the actual documentation in front of you and we kind of walk through it step by step together. Again, if you don't have it, obviously you can follow along, and this will give you kind of a brief understanding of what that document covers. If you don't already own this, I wouldn't suggest this is necessarily a document that you're going to need. It does give you a few breakdowns that are helpful, but it's not necessarily a required document for you to have, as compared to maybe like the ANSI B11 or the B11.19 standard, as well as like the NFPA 79 standard here that we've talked about. This standard more or less gives you the breakdown to understand why we use that type of controller, what the benefit is, what the breakdown of the actual controller is itself, and why it needs to be a safety rated controller versus like any other standard PLC. Even a dual redundant system isn't quite meeting the standard of a safety controller. So, excuse me, if that's something that you want to understand a little more of, obviously, then feel free to obtain this standard from like the ANSI store. Anyway, moving forward, so the in the introduction on this particular standard, they go through a really nice visual chart that gives you like a step-by-step process of when you need to use what standard or what technical report to guide you through it. So they give you obviously like some of the responsibilities, some of the hazards that come to play, and then when you're going to reference the ANSI B11.TR4 or technical report number 3, and then when you're going to reference the ANSI B11.19, and then continuing on down, you'll reference the NFPA 79, and then you'll finally come down to the ANSI standard B11.TR4 or the technical review number 4. You also have the option of using like a hardwired system rather than using some type of safety rated PLC or safety rated controller. The traditional way is we always would have done a hardwire system with the physical safety relay that would monitor the circuit or monitor the system rather than using a physical safety PLC that's configurable. Where you go switching more and more to the configurable systems because not necessarily the reliability, though they are well into the reliability standard side of it, it's the fact that they're becoming easier to troubleshoot when you have multiple systems connected to those. So definitely something to consider for your particular application. But let's go on and kind of look this over. So ANSI standard kind of gives us a definition of why we consider choosing this particular route rather than maybe using the safety relay or using some other kind of system. So first off, obviously, is the complexity of the equipment. So how many doors do you have on this system? So how many guard doors do you have? How many light curtains do you have? How many safety arrays, safety mats, pull ropes, emergency stop push buttons, etc. If you have multiple ones of those and you have to monitor all of those, obviously using a safety PLC is more of a simplistic design. Whereas in maybe a traditional old school system where we have multiple emergency stops, multiple guard doors, multiple pull ropes, and then light curtains associated in with all of that system all together, we now have to bring all of those into separate safety control monitored relays that all go back to maybe like a main monitor relay. And it produces a major cluster, takes up cabinet space, and uses up too much space, produces a lot more heat, etc. And so it just makes it more complex, and in a sense, it's harder to troubleshoot later on down the road. So we switched to something a little bit simpler to use and work with. We also have to understand our knowledge of of our people. So that's the people that are going to operate the machinery. That's the people that are going to troubleshoot it. That's the people that are designing the system. And that's anybody that could come in contact with that piece of equipment. What kind of dedicated system do we need? So are we having to dedicate it in those ways? Do we need to dedicate a light curtain individually? Do we need to dedicate a light curtain within the system altogether? What is our risk assessment telling us? So did we complete the risk assessment? Did we determine what we need, what we don't need? How that's going to affect and play into our circuitry, our system here, what safety level rating we're trying to target and hit. And lastly, the life cycle of the controller. So are we using a newer controller? Are we using an older controller? How long is this going to last? Is this something that's going to fail quickly? Is this something that's going to last a long period of time? What are we looking at for that kind of a system? So when we get into the safety side of it, we need to talk about what is the safety rating, or what is the option or opportunity of the safety controller itself. So the safety controller is designed to be in a fail-safe state. So what does that mean exactly? It means that the system is going to fail. If it fails in any way, shape, or form, it's going to fail in a safe position. So for instance, if you have a contact that's a normally open contact, and when it's powered on, so the emergency stops are cleared and the power on button has been pressed, it's safe to run and everything, that contact comes and closes. If for some reason this safety system fails, that contact could never fail closed. It would always fail in an open state or an open position. And then vice versa if it's a normally closed contact. What it would also entail is that it would prevent any type of operation if it's in a failed state. So if any of those contacts, so you would create more or less a monitored circuit, and we'll go through some of how that circuitry is designed in some other later videos down the road. But when that circuit is designed, it's designed so that if there's a monitoring circuit that fails somewhere along the way, or it understands that any other pieces failed within the system, that it will keep and prevent the system from re-engaging while it's in that failed state. Obviously, it won't have any type of automatic startup. It'll require some type of a manual startup, manual override, resetting all the e-stop buttons, or pull ropes, light curtains, etc. And then you'll have to trigger some kind of power on or reset kind of function. Yes, you can do automatic systems. That's not entirely the point of the automatic startup. The automatic startup means that when we power on something along those lines, that we're gonna require some kind of power on. It'll prevent a run when the system is in a shutdown state. So again, very similar to the operation of a failed state. So when it's in the shutdown state, it's not going to allow anything to run. It's totally disabled. It's totally shut down. When it'll prevent a run when the system is in the safety stop state. So again, you can't. That's the same as a safety relay on that particular point. There is that you can't run it when you've pressed an e-stop, when you've opened a door, whatever those things might be. You cannot run this system. And then one thing I really kind of want to point out to us is communications are completely acceptable as long as their latency will not affect the system. And if it should fail, it must fail in a safe state. So we do have systems out there, and I reference these because they exist. ABB has their JoCab safety, and it uses a special type of JoCab safety bus. And then you have, let's see here, you have like Keyence has multiple different bus networks that communicate across, minus their particular preferenced I/O link kind of thing. And then you have obviously like Allen Bradley systems use a lot of Ethernet, and then I do believe that Siemens is dabbling, well, I shouldn't say dabbling, they've developed it very well into the Profibus system for their safety communications. And then we even have the ASI or Aussie bus, however you want to pronounce that, and a lot of systems have been using that communications system for quite a while. And I want to say it's Beckhoff or something along those lines, but I couldn't quote that, and please don't quote me on that. But there's a few systems that have been using the ANSI bus for quite some time now. And then we're even starting to see, and I can't say Siemens is the one that's pioneering this, but there's some other companies out there that have really been going deep into using Surcos communications here recently. And that's been kind of a game changer as well because of the redundancy system that Surcos is using. Now, obviously, Rockwell's using their Ethernet IP, and they're using that in a redundancy system as well, and that's also very similar to the Surcos communication. So one of the things that comes into this play here, again with the safety PLC or the safety rating, is the need for the risk level. So at what level do you have? Do you have a high risk with a high occurrence? Do you have a low risk with a low occurrence? Somewhere in the middle, what do you have? So obviously you're going to have like your 0 category or your traditional B rating, category rating, and that's the lowest safety rating. It's almost non-existent. It's like putting a relay in there with a gate switch that's just a normal sensor, so it could fail. And then when it does, it may not protect you at all. Then you have a category 1 or a SIL rating of 0, and that's usually like a single channel, non-redundant. There's nothing there. It's a safety rated relay and it's a safety rated switch, and they're going to monitor each other, and that's all they're going to do. And there's no redundancy, there's no real true monitoring, but they're going to pay attention to what's going on with the switch. Then you have an SIL category of 1 or a Cat 2, and there is redundancy, and it can be single or dual channel. An SIL category 2 or category 3, so you do have the redundancy. There is a little bit of a monitoring system in there that's going to monitor for a fail-safe kind of system, and then it's all going to be dual or redundant, so it's a dual channel system. And then obviously you're going to have an SIL3 or a Cat 4, which is the highest level. I do know there's a lot of companies out there that are pushing for a Cat 4 system or an SIL rating 3, and that is the highest safety rating, and it is control reliable. Everything must be control reliable, and provided that everything is done redundantly, everything is going to be monitored to a T, and everything obviously is in a dual channel state. So you do have your auxiliary equipment, and they will be rated based on their external status. So I know like particular like some safety PLCs standalone are rated like a category 3 or an SIL2 or something along those lines. And then you'll have like sensors, interlocks, light curtains, pull rope, safety mats, array scanners, etc. All of those are going to fail safe as long as they're rated in that category. So some of those are going to be rated like a Cat 2 or an SIL level 1 because they're only going to be like maybe a single channel rated. Or you might have something that has a dual channel without a monitoring circuit, or you might have something that's a dual channel with a monitoring circuit. It all kind of depends, and it's going to depend obviously on your requirement for your particular project that you're working on. One thing I want to talk a little bit about is our resetting of the circuit. So resetting the circuit, we're going to talk about the big thing is like using a manual reset should be obviously considered. So the manual reset is going to be some type of a reset. So if I trip a light curtain, I have a reset button right next to it. If I trip an array scanner, I have a reset button next to it. If I trip the pull rope, I've got to go reset the pull rope with a little switch, and then I got to go over and hit a reset button to reset it and clear it. So something inside of the PLC program or the safety rated program is causing us to have to reset the system. Should we have a master reset? So traditionally in most manufacturing things we would call this a power on button. We're only allowed one power on button for the entire project that this is connected to. We can have multiple resets but only one power on button. A simple safety reset can be maintained in specified remote locations. Now that again goes back to kind of our topic number 1. We can have resets wherever we want, but we can only have one power on push button or enabling system. And then the system obviously should not be able or allowed to reset if one of the systems fails or failed air checking. So what are we saying there? It's that monitoring circuit. So if for some reason we have a normally closed contact on a gate switch that trips open, but for some reason does not reset properly when the gate switch is opened, that's considered a failed switch, and so it is failed in a fail-safe state and will not allow the system to reset because of its failure until it is either fixed, isolated, or reset somehow in some maintaining way. And last but not least, the most important thing is once you've completed your system, you need to redo your risk assessment to verify that you have met all of your proper criteria to make the machine or the equipment safe. And you need to validate and verify. Validation is a documented test procedure that has gone through step by step of verifying that each one of those pieces that's on your validation is up to standard or up to par of what your requirement is. So for instance, if I have a gate switch, I'm verifying that the gate switch will not allow the machine to run when it's open, but will allow the machine to run when it's closed. And if it's a monitored system, is also being monitored properly through the PLC. In order to validate that door lock, we have to go through all of those test procedures, verify that each one of those is working, functioning correctly, and then we are able to sign off on that gate switch's validation. We should do that for each and every single piece of equipment, of safety rated equipment that is on that particular piece of manufacturing equipment or production line or whatever that might be. And we need to go through all of that anytime an adjustment or change is made to that particular piece of equipment. This is a procedure that all of us should follow to make sure that all of our equipment is up to a true safety rated standard. If you have any questions, please feel free to drop a comment in the bottom, or obviously like on the video, and then I will get back to you as soon as I can on those comments. So thank you all for watching, and stay tuned for additional content and information.